Welcome to The Explainer. Today we're diving into the massive, high-stakes world of heavy industrial equipment. You know, those giant refinery tanks, towering pressure vessels, and endless miles of thick steel piping you see at industrial plants. From the outside, they look invincible, right? Just completely solid. But what if I told you that locked right inside that incredibly strong steel, there's often a hidden, invisible enemy actively trying to tear it apart from the inside out? It's a pretty crazy engineering mystery, and honestly, by the end of this explainer, you're going to look at the industrial world around you in a totally different way.
To fight this invisible enemy, engineers do something that sounds, frankly, completely backwards. They take these massive, incredibly heavy steel vessels that they just spent weeks perfectly welding together, and they bake them in giant industrial ovens at blistering temperatures. I mean, it sounds absolutely crazy. Why on earth would you blast a brand new, heavy-duty steel structure with intense heat? Well, it isn't a mistake, and it's definitely not just a finishing technique. It is a vital survival mechanism for the metal. And to understand why we do this, we've got to zoom way in and look at what happens when we weld steel together.
Okay, so let's think about the metal itself. Imagine your original, unaltered metal plates. They're just sitting there, totally relaxed. But to join them together, welding uses extreme, super localized heat to melt the edges. Now, if you just heated up the middle of a piece of metal without attaching it to anything, it would naturally shrink as it cools down, causing the edges to warp inward. But when we actually weld two plates together, they're fused. That molten metal in the middle cools down and desperately wants to shrink, but the huge amount of cold steel surrounding it simply won't let it. So you end up with this massive, vicious tug-of-war. The outer edges are being pushed out, experiencing what we call compressive stress, while the center weld is stretched unbelievably tight. It literally traps tensile residual stress right there in the middle of the joint.
If all this physics of thermal expansion sounds a bit abstract, let's think about it like this. Imagine you've got a really stretchy t-shirt, and you decide to sew a completely non-stretchy, super tight patch right in the middle of it. Even if you just lay that shirt flat on a table, the fabric around that patch is puckering, pulling, and stretching, right? It's under constant, invisible tension. Well, that is exactly what's happening inside thick steel plates after a weld. There doesn't even need to be a drop of liquid or an ounce of pressure inside the tank yet. The metal is already pulling itself apart. And here's a really interesting twist. The danger isn't even necessarily in the weld itself. The focal point of all this crazy tension hides in a specific area called the haze, or the heat-affected zone. This is just the strip of base metal immediately surrounding the weld. It didn't actually melt, but it got so shockingly hot that its internal structural properties were fundamentally altered. That specific zone becomes the ultimate battleground where all those invisible pulling forces concentrate. So, let's officially put a name to our invisible enemy, tensile residual stress. These are the internal pulling forces that are permanently trapped inside a material after welding or physically bending it. And I really want to emphasize this part. This tension exists even without any external loads applied. A tank could literally be sitting completely empty in a parking lot, and yet inside that heat-affected zone, the steel is acting like a permanently stretched rubber band, just waiting to snap.
Now, how does this go from bad to a total catastrophe? Well, if you take a steel vessel completely loaded with this trapped stress, and you put it into an active industrial environment where it's exposed to corrosive stuff, like harsh acids or gases, you've just created a perfect recipe for disaster. This combination triggers something called stress corrosion cracking, or SCC. Basically, the corrosive chemicals ruthlessly attack the exact microscopic points where the stress is pulling the hardest. The metal literally unzips and tears wide open, causing massive, sudden equipment failure.
The thermal cure, solving the stress problem with Post-Weld Heat Treatment, or PWHT.
So, how do we disarm this ticking time bomb? When is this giant thermal massage actually required? Well, in heavy engineering, there are really strict rules governed by international standards, like the ASME code. For standard carbon steel, the absolute golden number you need to remember is 38. Once the thickness of that steel plate hits 38 millimeters, the risk of trapped stress gets so high that post-weld heat treatment becomes absolutely mandatory. You simply cannot skip it.
But, this is engineering, so there's always a catch. If the fabrication team doesn't carefully preheat the metal right before they start welding, the surrounding cold steel will cause a massive temperature shock. And because of that extra shock, the safety threshold actually drops. Without preheating, the code says you have to bake the vessel if the steel is just 32 millimeters thick. It's an incredibly strict balancing act of heat management. Now, seeing how beautifully PWHT solves this stress problem in carbon steel, you might be thinking, great, it's a universal cure-all. Let's just bake everything. Well, hold on, because we're about to hit a massive plot twist. Is heat always the cure for residual stress?
The answer to that is a hard, resounding no. And here's the dramatic contrast. Carbon steel absolutely loves heat treatment. It needs PWHT to relieve stress safely. But if you take a vessel made of stainless steel and try to put it through that exact same baking process, you are going to completely ruin it. For stainless steel, PWHT triggers this terrifying chemical breakdown called sensitization. It essentially destroys the metal's natural ability to fight off rust and corrosion.
Let's break down exactly why this happens, step by step, so we can see how stainless steel loses its superpower. First, the heat treatment slowly warms up the stainless steel. As it's just sitting there baking in the oven, these tiny trace amounts of carbon inside the metal wake up. They get highly active and actually start binding with the chromium. Because the carbon is suddenly hoarding all the chromium, the metal loses its vital, invisible anti-corrosion shield on the surface. So when that vessel is finally put into service, severe, rapid cracking happens almost immediately.
To put this into perspective with some actual numbers, high-quality stainless steel relies on having about 18% free chromium perfectly distributed throughout the metal to create its protective layer. But during sensitization, because the carbon acts like a thief and steals that chromium, the free chromium levels in those local areas plummet from 18% all the way down to just 6%. The stainless steel is completely starved of its armor, leaving it totally defenseless. And making this specific heat treatment mistake with certain stabilized grades of stainless steel, like SS321 or SS347, results in this chillingly precise type of failure. In the industry, they call it a knife line attack. Since the chemistry breaks down right at the boundary of the weld, the corrosion slices through the metal in a microscopic, razor-thin line that runs perfectly parallel to the joint. It literally looks like someone took a surgical scalpel right to the heavy steel.
Beyond welding, stress relieving, or SR, for mechanical deformation. Now, welding actually isn't the only way to trap dangerous stress inside metal. Physically forcing thick steel into a new shape causes the exact same type of internal chaos. It's important to clarify the difference here, because the actual time the metal spends in the oven looks totally identical. Post-Weld Heat Treatment, PWHT, is specifically done to relieve the residual stress created by thermal damage, like the extreme heat of a weld. Stress relieving, on the other hand, uses the exact same thermal baking method, but it fixes the mechanical damage caused by aggressive physical bending, pressing, or rolling of the steel.
So how much physical bending is too much bending? The engineering rule of thumb here relies on something called extreme fiber elongation. Basically, if you take a thick plate of steel and bend it so aggressively that the outer fibers of the metal stretch by more than 5%, you've locked in way too much mechanical stress. Just like that 38mm rule we talked about for welding, if you cross this 5% stretch threshold, that metal absolutely has to go into the oven for stress relieving.
Ultimately, what all of this boils down to is incredibly high-stakes communication. The mechanical engineers designing these plants have to clearly and explicitly spell out the exact PWHT, or stress-relieving requirements, right on their datasheets. They hand those over to the vendors building the equipment. From there, dedicated inspection teams have to meticulously verify that the fabricators are following the code to the letter. Because think about it, too much heat ruins stainless steel, and too little heat leaves carbon steel as a ticking time bomb. There is literally no room for error.
It really makes you look at the engineered world differently, doesn't it? These static, silent structures that we drive past every day are actually holding back immense internal forces. They're only tamed by a really profound understanding of physics, chemistry, and heat. So the next time you see a massive industrial plant or a towering refinery, ask yourself, how much invisible stress is safely locked away in there, all thanks to a giant oven? It's a pretty fascinating hidden reality. Thanks for hanging out for this explainer, and keep questioning how the world around you is built.